Hello everyone, welcome to this presentation where we'll take you through the aviation accident analysis for the last 53 years. We'll talk about how we collected our data, how we prepared our data, and then what information we're able to get out of this data.
Let's get started. Let me introduce you to the team first. Masood Ahmed Siddiq, Zibal Jafri, Mustafa Ahmed, and myself Raghav. All of us are grad students in the Department of Management Information Systems at Oklahoma State University. The agenda of this presentation is going to be like this. First, we'll talk about the methodology, then introduction and scope and objectives, then data preparation and exploratory analysis. After that, we'll talk about the models, and then we'll end with the original versus final product and the lessons learned. Before I give you an introduction about the project, let me talk about CRISP DM methodology. In CRISP DM methodology, we have 6 phases. First is business understanding, data preparation, model building, testing and evaluation, and the last phase is deployment. We have used this methodology in our project. Let me give you an introduction about our project. According to National Transportation Safety Board statistics, in 2014, the number of aviation accidents increased by 15%. Despite US government efforts to reduce aviation accidents, there was an overall increase in the number measured against flight hours nationwide. The project delves to find out relationship between aviation accident factors and the number of injuries. This will enable the aviation industry in making future decisions to reduce these accidents to the least possible count. Now let us talk about the scope and objectives of our project. Analyzing the civil aviation accidents for the past 53 years, identify the main cause for these accidents which cause loss of life, analyze the density of accident across different regions which are prone to these accidents, look for scenarios which caused huge loss of property and life, and look for possible ways to avoid them. Let us move to the data preparation phase. The data was collected from the National Transportation Safety Board website. Primary data set consisted of 63 variables and 70,000 records. Data was consolidated using Microsoft SQL Server Management Studio. We did data cleaning and data transformation mainly through the SQL Studio. We removed the null values for all the variables. We used various SQL features in SQL like ltrim, rtrim to remove the leading and trailing blank spaces. We created new variables like total injured, which was a sum for all the different types of injury variables. We transformed some categorical variables into numeric variables to use them as target and predictors in our models. We did data reduction. We used sample data from 2008 to October 2015, neglected unimportant variables like accident number, registration number, etc. We assigned NA to some null values and then neglected them. The final data set we had consisted of 36 variables and 11,000 observations. Now Zibal will take you through various visualizations that we built to describe our analysis.
Thanks Raghav, it was indeed a very good introduction. I'm Zibal Jafri and I'll be explaining the descriptive statistics and explanatory analysis part of the project.
I will be explaining the results of the explanatory analysis. The geographical figure summarizes aircraft accidents that occurred in different states of the US. As we can see from the figure, all the states are coded in different colors to display the total number of fatal injuries each state had to bear. The states colored with dark gray, gray and light gray are the ones which faced maximum casualties during the unfortunate occurrence, whereas the states colored with white and different shades of magenta red faced less casualties. We can observe that the states California, Florida and Texas have the highest number of fatalities, whereas other states have a lower figure comparatively. Moving on to the next figure. This pie chart shows the fatalities figure due to the accidents and their causes. After analyzing the accident data, we observed that majority of accidents were caused due to human errors. Now, human error can be further classified into different subcategories such as pilot error or other human error. A pilot error represents accidents where the error was on the part of the pilot, whereas Other human error includes air traffic control errors, improper aircraft loading error, fuel contamination, and improper maintenance methodology. The second most common cause of aviation accidents is mechanical error, which is shown in the green color in the pie chart. Bulk of the remaining accidents are caused due to bad weather, and very few accidents are caused due to organizational failure. Moving on to the next figure. This line graph shows the yearly trend of total fatalities based on the engine type used. From the plot, we can observe that most of the accidents was reported for the aircrafts which were using reciprocating engine, which is shown by the red line in the graph. Aircrafts equipped with turbojet engine had least fatalities, as shown by the brown line in the graph. We can also observe that the fatalities caused due to aircraft accidents using turbofan proliferated in 2013, but it won't be nice and wise to conclude that the type of engine used that particular year was the root cause of the accidents, as the fatality figure never increased but went down thereafter. All other engine types used in the aircraft have more or less same number of injuries, which is not much during these years. So we can infer that the aircrafts using reciprocating engine are more vulnerable to fatal accidents as compared to the aircrafts using other engine types. Moving on to the next figure, which is a bar graph. This shows the accidents at different phases of flights when it occurred. We can observe that most of the fatal accidents occur during the approach phase of flight. The second most common phase of flight vulnerable to fatal accidents is the takeoff stage. So, we can infer that most fatalities take place during the approach or the landing and takeoff or the departure stages of flight. Now, this is understandable as during these two phases the aircraft is close to the ground and is at a susceptible position than during other phases of the flight. We can also observe the least risky phase of flight is the taxi stage, where the aircraft is moving in the ground just before the takeoff. The model techniques. The model techniques part of the presentation will be explained by my teammate Masood Ahmed. Thank you.
Thank you Zibal for a detailed explanation. I'm Masood Ahmed. I'll be talking about the models which we have created for our project. Before that, let's have a quick recap. So far, we have learned about the methodology adopted for the project, the idea behind choosing this topic, the scope and objectives of our project. Also, we have seen some challenges faced in gathering the data, and also we have explained the analysis of our project. With this foundation, we go ahead and make few models. Let's have a look at them.
First, I will be explaining about the child tree model. The child tree provides a tree-based classification model which will classify cases into groups, predict the target value based on the input predictor variables which are independent. Our target variable in this model is total injured, which is nothing but the total number of people injured in accidents. As most of our predictors are multiple levels, it helps us dig into the various possible groups of the independent variables and give a clear picture of the importance of independent variables on the behavior of target variables. We will be able to find out the importance of predictors and also predict the target variable based upon this. All the possible splits of the predictor will be examined and the more important predictors are decided with the help of this model. Now let's go ahead and have a look at the results which this model gives us. As you can see, a broad phase of flight followed by the schedule and flight plan activation are the most important predictors. So, what do these infer? Careful study of these variables might lead us to some findings which help us in providing recommendations to the aviation industry. Few phases of flight are prone to accidents. Extra carefulness during these phases might minimize the accidents. Regarding flight schedule, if a flight is not on schedule, it might increase chances of accident. How? Due to this unplanned flight, the ground crew is under pressure as it might have many more flights to handle at the same time, and the same is the risk when the flight is not as per its plan and it might lose track of this route. So this is all the child tree model explains. Now let's go ahead and see our next model, which is nothing but linear regression model. We use linear regression modeling for finding relationship between dependent variable and one or more independent variables. Especially in our project, we have got many independent variables, and it is very important to study these variables, which will help us to decide on selecting few variables which will help in analyzing our target variable. In this particular graph, we can see that the graph is linear if we consider only the first 2 points, because the last point does not have much more significance here. So what can we learn from this graph? Majority of injuries and accidents are seen in the flights used for public, personal, external load, ferry, business glider purposes, and etc. So what can we learn from this? The flights meant for these purposes have to be built much more stronger to withstand any conditions, and every possible precautions must be taken. Moving on to the next slide, which is our result of a linear regression model. This is another graph. What interests us in the is the relation between last 2 points, which display a linear relation. Landing, approach, cruise, descent are the phases of flight during which majority of fatalities are observed. So what are the takeaways here? The whole crew controlling the flight must be extra careful during these phases of flight, which are prone to accidents, and make necessary technical changes as possible. A much more deeper analysis with more variables attached can reveal interesting facts. The rest of the models will be explained by my teammate Mustafa. Thank you.
Thank you, Masood, for explaining the two models. I am Mustafa Ahmed, and I would be explaining the regression model, original and final vision of our project, and also the lessons learned during the course of this project.
I am going to explain about the multiple regression model. This is the last model that we have used in our project. The model is built using R programming. The target variable that we have used is total injury, and the predicted variables are flight hours, flight plan activated, number of engines, aircraft damage, and runway length. Before settling on the above predicted variables, we used the variables such as aircraft maker to determine which airplanes caused the maximum number of injuries. But there were more than 30,000 aircraft manufacturers in the database, which did not give us correct visualization. So we had to discard aircraft manufacturer from the independent variables and concentrate on other independent variables to determine how they affected the target variable total injury. The main assumption of this model is that the target and predicted variables show a linear relationship. By using pairs functions, the linearity of the variables is plotted as can be seen in the figure. The variables such as number of engines, flight hours, and aircraft damage have a linear relationship as can be. Now let us check the normality assumption. The histogram of the residuals does not show a normal distribution. For the regression model, this is not a best possible scenario. The numerical value of the dependent variables were very small, so the variance could not be distinguished from the residual plots. There were no outliers in the variables considered in the model. Now let us see the results. The p-value of the regression model is 9.469 e to the power of minus 6, which is statistically a small number. This is less than the alpha value of 0.05. The p-values of aircraft damage and number of engines are 0.00969 and 0.005231, which are less than alpha. So these are our significant variables. The adjusted R-square value given by the model is 0.1957, which is considerable. The adjusted R-square and F-test make it easy to explain the observed relationship and explanatory power of the model. Coefficients of the independent variables explain the direction of relationships with the target variables. The dependent variables in the model which are statistically significant, that is, whose p-value is less than 0.015, are aircraft damage and number of engines. The dependent variables that are insignificant in the model are runway length, flight plan activated, and flight hour. To predict the dependent variables, the model is showing that the aircraft damage and number of engines are helping to predict the total number of injuries in the accident, whereas the dependent variables, runway length, flight hours, flight plan activated, are not providing the predicted value of total injuries. The model also explains an accuracy of 19.57%, which is considerable. Now let us see the original vision of the project and the final product. The original vision of the project was to explore the reasons for the accident and also to identify the underlying causes of the accident. The other objective was to prevent the financial losses to the aviation industry by identifying the causes and also to prevent the reoccurrence of these accidents. And the final product that has been delivered by us was by building three predictive models to address our objective. We succeeded in achieving our project objective partially. We were able to find out the contributing factors of the variables and also to build a regression equation that helped to calculate the target variable total injury. Moving ahead, the lessons that we have learned from this project are: we understood that the data preparation is the most important phase of this DM methodology. Descriptive statistics and exploratory analysis on the data can sometimes be misleading. The other lesson that we have learned was that the objective of the project may change during the course of the project. We have to have sufficient bandwidth to adjust to the changes that may come during the course of the project. We have also learned that the time management and team coordination is vital for the delivery of the project. And the final lesson that we have learned was the model should not only be chosen based on statistics but by utilizing the domain knowledge on the subject. We had a wonderful time doing this project. We would once again like to thank Dr. Hammer for giving us this opportunity. We wish everyone a Merry Christmas and a Happy New Year. Thank you. For any queries or feedback, you can contact us at the emails provided on this slide.